Good morning, children. Welcome back to Ican Physics Academy. Now, in this class, we are going to see CBSE question, that is PYQ 2021 55 bar 4 bar 1. Question number 33. Let's enjoy the class. Question number 33. A. First question. A germanium crystal is doped with antimony. With the help of energy band diagram, explain how the conductivity of the doped crystal is affected. Okay, when the germanium is doped with antimony. Okay, the valence electron for germanium is 4 electron. But the valence electron for antimony is 5 electron, because the antimony is the pentavalent material. Pentavalent material. So when the pentavalent material is doped with the germanium, so that the electrical conductivity increases. Electrical conductivity increases. Okay. So when the antimony is doped with germanium. Okay, so what is the valence electron for antimony? Is 5 electron. So this antimony ready to give the electrons with the neighboring germanium. So 1, 2, 3, 4. Now we are having 1. The excess of 1 is here. So antimony has 5 valence electron. 1, 2, 3, 4, and the excess of 1 electron. Germanium has 4. It is ready to share with the neighboring. Okay, so 1, 2, 3, 4. This germanium, 1, 2, 3, 4. For this germanium, 1, 2, 3, 4. For this one, 1, 2, 3, 4. So when we are taking into account of this one, the antimony gives 1 electron to this germanium and get 1 from. One giving, one getting, giving, getting. So mutual sharing of electron. So it forms the covalent bond. Covalent bond. But we are having excess of electron. It is ready to donate. So automatically the electrical conductivity increases. For this, what is the energy level diagram? Okay. So this will be the valence band, and this will be the conduction band. Okay. The gap between the two energy levels is called the forbidden energy gap. Forbidden energy gap. So it is ready to donate. Ready to donate. So energy level is well above the valence band or just below the conduction band. So this is the donor level. Okay, do you get it? Do you have any doubts? No doubts. Okay, the second question. Briefly explain 2 processes involved in the formation of PN junction. Okay, now the second question. Okay, so what are the 2 processes? So one is a diffusion. One is diffusion. Another one is a drift. Okay, another one is drift. In the formation of PN junction. Okay, so let us consider first method, diffusion. Diffusion. So when 2 type of material, that is P and N. So P type, it is formed by 3 electrons. Okay, so it is ready to accept. Ready to the majority charge carriers are holes. On the other hand, in N region, we are having 5 electrons. It is ready to donate. Ready to donate. So, excess of electrons. So, the N region, which has excess of electrons, is denoted by positive with a negative. Here, the negative with a positive. So, positive, negative with a positive. Here, positive with the negative. Okay. Now, due to majority charge carrier concentration, the electrons from N region crosses the junction, enter into the P region and form the region closer to the junction with a negative ions. Now the positive ions from the P region crosses the junction, enter into the N region and form the region. Okay, so the region which consists of immobile ions, then it's called a depletion region. So this is the formation of PN junction by diffusion method. Okay, do you get it now? Do you have any doubts? No doubts. Okay, so next one is a drift. Okay, so this one is the PN junction diode. Okay, so because of formation of the junction, it produces the electric field. Okay, now in the P region, as we said, the negative with a positive, negative with a positive, negative with a positive. Okay, here we are having positive with a negative. Okay, so because of this field, the electrons from the P region are drifted towards the N region. Okay, on the other hand, the holes from the N region, because of this electric field, drifted towards the P region and it formed the region once again with a positive and a negative ions which are immobile, and the region is called a depletion region. So this is the formation of PN junction diode by diffusion method and a drift method. Okay, do you get it now? Do you have any doubts? No doubts. Okay, question number 33 and the third question. What will be the effect of forward biasing and reverse biasing be on the width of the depletion layer in PN junction diode? Okay, so once again we can consider the same. Okay, so when the P side is connected with a positive terminal, then it is said to be forward bias. So when we are giving the forward bias, here we are having positive, here we are having holes. The holes are having also positive. So positive, positive repel each other. When the repulsive force increases, then automatically the holes from the P region crosses the junction. On the other hand, when the N region connected with the negative terminal, then negative repel each other, then these negative electrons crosses the junction. So it becomes mobile region. So when it is a forward bias, then the depletion region decreases. Okay. So on the other hand, when it is a reverse bias, the depletion region increases. Okay. Do you get it now? Do you have any doubts? No doubts. Now, question number 33, or question B, first question. With the help of a circuit diagram, briefly explain the working of a full wave rectifier using PN junction diodes. So, a rectifier or a rectification. So, what is rectification? The process of converting AC voltage or AC current into DC voltage or DC current is called a rectification. The device which is used for a rectification is called a rectifier. So diode can acting as a rectifier. Okay. So the full wave rectifier consists of two diodes, diode 1 and diode 2. Okay. Now it's a P side and it's N side. Okay. Now it can be taken as diode 2. Now the two P sides of the diode is connected with the secondary of the transformer. Okay. Now the primary of the transformer is connected with the AC source. Okay. Now the N side is connected with a resistor, or it's called a load resistor. And here the transformer is center tapped. Center tapped. So for output, we can take like this. Okay. Do you get it now? Do you have any doubts? No doubts. Okay. So when I am giving the primary voltage, so that it produces the secondary voltage in the secondary coil. Suppose it can be taken as S1 and it is S2. Okay. So for the positive half cycle, positive, negative. The S1 is positive and S2 is negative. Okay. When the positive connected with the P side, so the D1 is a forward bias, then it gives the output. So we can take the output. At the same time, the negative is connected with the P region of the D2, which gives a reverse bias, which does not allow. Okay. So during the negative half cycle, now it becomes negative and it becomes positive. Now S1 becomes negative and S2 becomes positive. Now the negative connected with the P, then it gives a reverse bias which does not allow the current. At the same time, the positive connected with the P side of the D2, which gives forward bias and which allows the current. Okay. So we are getting the DC. Okay. So alternatively it flows. Then AC. Then it is unidirectional. So it is DC. So AC is converted into DC. So what is the efficiency of the full wave rectifier? That is 81.2% is the efficiency. Okay. Do you get it now? Do you get it now? No doubt. So here the transformer is center tapped. So why it is center tapped? When the P region is connected with the positive at any instant with respect to the center tap, then automatically S2 will be negative. On another hand, when it is positive with respect to the center tap at any instant, then automatically the D1 gets negative. Okay. Do you get it now? Do any doubts? No doubts. Okay. So 33B, second question. Draw VI characteristics of a PN junction diode. Explain how these characteristics make a diode suitable for a rectification. Okay. Second question. VI characteristics curve. Okay. So now voltage is taken along x-axis and the current is taken along y-axis. For forward bias, so when the voltage increases, initially the current will be 0. Why? Because of potential barrier. So after that, it slowly diffuses into the potential barrier. So it causes some current. Once the depletion region decreases and disappears, then it allows the maximum current. So graph will be like this. So when it is forward bias, it allows the current. Now only we see when the diode is a forward bias, it allows the current. Okay. So that it is used for a rectification or used as a rectifier. Okay. On the other hand, when it is a reverse bias, when the voltage increases, okay, so automatically the depletion region increases and it does not contact. Okay, so like that it comes. Okay, but a few electrons can diffuse into the potential barrier and it crosses the depletion region and it causes the microamperes of current because of leakage current. Okay, so because of this, it does not allow the current. So that when D1 is a reverse bias or D2 is in reverse bias conduction, it does not conduct. Okay. So for that purpose only we are using a diode for a rectification. Okay. Question number 33B, third question. Carbon and silicon have the same lattice structure. Then why is carbon an insulator but the silicon a semiconductor? Carbon and silicon. So what is the atomic number for carbon? 6. For silicon, it will be 14. Okay. Now, carbon, it has 2 electrons in the K cell and 4 electrons in the L cell. At the same time, for silicon, 2 electrons in K, 8 electrons in L, and 4 electrons in M cell. Okay. So 4 plus 2, 6 electron. Okay. 8 plus 2, 10, 10 plus 4, 14 electron. Okay. But the valence electron is in L cell for carbon, which needs more energy to take these 4 electrons from the orbit, so that the carbon acting as a insulator. At the same time, silicon, it has 4 electrons in the M cell, which requires very less energy to liberate these 4 electrons from the bond. Okay, so that it acting as a semiconductor. Okay, do you get it now? Do you have any doubts? No doubts.